And this talk is based on joint work with Brad Week. So first, I would like to just quickly go over the concept of Bergman kernel and Bergman projection, even though I assume everyone right here is familiar with it. Let omega be a domain in Cn. The Bergman space will be the space of square integrable holomorphic function. We're going to use notation A2 omega. The Bergman projection is the orthogonal projection from L2 to A2. And the Bergman kernel is the kernel function associated with the Bergman projection that reproduce every element in the Bergman space. And also the positive Bergman operator will be the operator that has a similar integral expression, except the kernel function in this case is the absolute value of the Bergman kernel. Let me spend some time to explain the matrix value weight setting, which is what we care about in this talk. So when it comes to a matrix valued weight, we are referring to a locally integrable function on omega. So the input will be points on omega, while the output will be positive semi-definite d by d matrices. And for our convenience, we'll also assume this W is positive definite almost everywhere. So even though in principle we allow at some point the function is positive semi-definite, but in most places it's positive definite. And then the weighted space associated with this matrix value weight will be the space of vector valued measurable function. So equipped with the following norm over, which is the integral over omega, with the integrand being the inner product of WF with F. Since W is positive definite, therefore it makes sense to make it a norm for this space. And when it comes to the Bergman projection, for example, on such a space of vector valued function, to make sense of it, basically what we need to do is just to apply the regular Bergman projection to every component of the vector valued function. So basically, when we talk about the Bergman projection in this vector valued function space, we're just looking at a matrix operator with each entry on the diagonal being the Bergman projection. Okay, and last but not least, we're going to use this left angle, right angle notation for the average of a function over a subset of omega, and also for the average of the matrix over a subset of omega. Any questions so far? Okay. Now, before I get into the Bergman setting, allow me to mention the matrix Markov A2 setting, which I will also do a comparison later on. Okay, so look at the simplest case over the real number axis. The Markov A2 weight is defined by the following formula right here. Well, we are taking the supremum over all intervals that are on the real line, and the quantity we'll look at will be the matrix norm square of this product of these two matrices. Well, each one will be the square root of the average of a matrix over the interval. Okay, so if you are familiar with the Markov, the scalar Markov A2 weight, you will see that in the case, well, the matrix is 1 by 1, which means it's the scalar case, then you don't need to worry about the matrix norm anymore, and you can bring the power 2 to the inside, and that exactly will give you the scalar A2 characteristic. As a comparison. Okay, so this is really a definition that generalizes the scalar case. It turns out this is the correct condition to characterize weighted space on which many of the operators are bounded. A result by Trail and Wahlberg in '97 showed that the Hilbert transform is bounded on this weighted space event only if this matrix weight W is A2 weight is satisfy this condition. Similar result will also obtain for other operators such as like vector value version of maximal operators, Calderon-Zygmunt operators, and so on. As to the norm estimate, there are also people making progress recently for various operators in the matrix weight setting. And one of the best results obtained for operators such as the Hilbert transform was due to Nazarov, Peter Michael, Trill, and Volberg in 17. Well, they show that the norm of the operators is controlled by some constant that depends on the size of your matrix and multiply with the A2 characteristic to the power 3/2. Okay, and so right here, as you can see, the power right here is 3/2 for the Hilbert transform. As you will see in our estimates for the Bergman projection, the power we obtain is a value that is slightly larger, and I'm going to explain why is that fairly soon. Now back to the Bergman setting. For the scalar case, we know that the correct condition to characterize the weighted space on which the Bergman projection was bounded is the Berkeley-Bonami condition. Well, they show the equivalence of the three statements right here. And the Berkeley-Bonami condition is, like Brad mentioned, the Berkeley-Bonami condition is a condition that is similar to the Markov AP condition, except in this case, the average is taken over those Carlson tent, TZ. Well, the tent could be chosen to be the entire ball in this case, if it's the unit ball case, or to be the tent that to be a subset that touches the boundary in this case. And we're considering the average over this class of subsets of the ball because they also reflect the singularity of the kernel function in the correct way. Just like the matrix A2 condition, we can also take a look at the analog matrix B2 condition, and here's the definition. When we are here's the condition for the unit disk. If W is a matrix value weight over the unit disk, and we have the following condition for the matrix B2 weight. Well, as you can see, the inequality looks very similar to the matrix A2 condition, except in this case, the average is taken over those Carlson tent instead of the intervals on the real line. Okay, and when it comes to characterizing the weighted space for the Bergman on which the Bergman projection is bounded in the matrix weight setting, the results is due to Element and Constantine in 2012. Well, they not only showed that this matrix B2 weight condition is the correct condition for the boundedness of the operator, but also they obtained the following norm estimate. If you look carefully, you will see that the constant arrow right here does not have the subindex D, which means actually what they showed in their papers is more. Well, actually they consider also the operator valued weight, which means in this case the vector valued function could have range in a Hilbert space of infinite dimension instead of just a finite dimensional CD. Okay, another remark I like to make about their result is that their result is on the unit disk, which means their proof relies heavily on uses a lot of nice property of the disk. Well, they use like the circular property of the disk, and in this setting, they are also able to relate the weighted norm of the holomorphic function to like the derivative of the norm of the derivative of the holomorphic function. Therefore, it's not that obvious to us how to generalize their result to like a more general domain directly using their technique. Nevertheless, we are able to extend Edelman and Konstantin's result for matrix weights to more general class of domains, and also we improve the estimate they have. Okay, so this is a result by me and Bradwick in 2020. Well, we obtained the following norm estimate. As you can see, the power we obtained right here is improved, which is 2, and also our estimate holds true for wide class of domains, like the bounded smooth domain that belongs to cases such as strictly pseudo-convex domains, pseudo-convex domain of finite type in C2, and convex domain of finite type in Cn. Okay, but still, since we use some of the argument from harmonic analysis, therefore, in our technique, the constant shown up right here will still depends on the size of the matrix, and therefore, our result doesn't cover the operator valued matrix weight, operator valued weight case. Okay, but one could also compare our result back to the result, the best known result for example, the Hilbert transform. Well, the estimate is something like this, while the power is 3/2. So, so right here, I would like to explain a little bit about why we don't quite get 3/2 right here, like the technical difficulty involved when it comes to this matrix weight setting. There are several technical details involving our proof, but since the time is limited, I'm just gonna focus on one of them, and which also reflects some of the differences between the Berkeley-Bonami constant and the Markov constant. Okay, so a crucial ingredient in showing many of the results for the matrix A2 weights is the so-called reverse Holder inequality for the scalar A2 weight. Okay, it basically says the following. Still, I'm just using the real line case. If the scalar weight, mu in this case, is A2 weight on the real line, and then the average of some power of mu over any interval actually can be controlled by the average of mu. Okay, so it's kind of like you're just doing the Holder inequality in the reverse direction, because on the left-hand side, right, you have a larger power in this case. Okay, unfortunately, and one of the reasons they would use this formula right here is useful in the matrix weight setting is because in many situations one would like to separate the matrix from the vector. The one way to do it is just apply the Holder. But if you apply the Holder, chances are you are going to increase the power of W, which is not good, because if you look back to the constant we want right here, you are not allowed to randomly just change the power of W right here. However, if you have the reverse Holder inequality, basically you can reverse the process, and therefore the arguments would still work. Unfortunately, this inequality does not hold true for the B2 constant, for the B2 weight. And here I provide an example on the unit disk. So if you look at this example right here, the weight I provide has a singularity at origin. However, I set it up in a way so that this function is still integrable on the entire disk, while if you raise the power of this weight by a little bit, then immediately it becomes not integrable. Therefore, if you look at a similar inequality right here, on the right-hand side, it's always going to be something that is finite, while on the left-hand side, you're going to get something that blows up, which will fail this inequality. Okay, and that actually reflects one of the differences between the A2 constant and B2 constant. For the A2 constant, you are just taking the average over all the intervals, while for the B2 constant, because, for example, the Bergman kernel on the unit disk only has singularity on the boundary diagonal, therefore you always consider those subset that touches to the boundary, which makes the B2 condition to not that good at controlling the singularity that occurred within the disk. And this example exactly reflects that. And then the question is, well, how to get around this? Once we realize the issue could come from the blow up of the weight within the domain or within the disk, then one could guess one may find appropriate condition to let the B2 weight to satisfy the reverse Holder inequality. And the result by Animan, Porter, and Regula in 19th basically says that as long as you make sure the top hat, when you are considering the top hat of each Carlson tent, and the value of the weight, the value of the B2 weights are about the same on the top hat, then still this B2 weight would satisfy the reverse Holder inequality. So by saying that on the top hat, the B2 weight behave the same is kind of just ruled out the possibility that you're going to have a blow up point in the interior in this case. Okay, and inspired by their results, we're basically able to construct a step averaging weight, fancy W, using the original given weights W right here. So what we do right here is we're considering a partition for the unit disk, for example, which Brad has just mentioned in previous talk. Right, this kind of construction. Yeah. Sorry. And then keep going. And then based on a given weight W, we'll just define this new weight W, which is the sum of the average of this little weight of W right here over those dyadic boxes in this decomposition, multiplied with the indicator function supported on the set. Okay, and the constructed weights in this setting satisfy various nice property. First, we can relate the B2 constant of this new weight back to the B2 constant of the original weight. Second, because this each of this little set right here are disjoint, therefore, when we're just considering this fancy W on the top half, each of this little set right here, it's just a constant matrix, which means the matrix doesn't change on those sets. And therefore, when we are relating them back to some of the related scalar weight, the corresponding scalar weight would also behave like a constant on those top half, and therefore satisfy the reverse Holder inequality, and hence the technique from harmonic analysis. And then the rest of the proof can be outlined as the following. Sorry, what's going on? First, just like Brad mentioned, need several collections to cover all the sets in the unit disk by doing a rotation in this case. And similarly, we need to do similar things right here by using finite many collections like the fancy T we had in previous slides. We are able to establish this estimate for the weighted norm of the holomorphic vector valued function f. Well, the submean value property is applied in this case. And as a consequence of that, by the duality argument, we can relate the weighted LP norm of the projection on the original weighted space to the weighted LP norm of the Bergman projection on this new weighted space with a bunch of fancy W right here. And then since each fancy W can be related to a scalar B2 weight satisfying the reverse Hölder inequality, we can adapt the technique from harmonic analysis to show that the projection, the weighted projection on this new weighted space is controlled by this B2 constant to the power 3/2, and then that inequality together with the inequality in the previous step give us the result we had in the theorem. Okay, so that's basically the sketch of the proof. Last, I'd like to mention some of the possible direction for generalization. First, our result right here is mainly focused on P equals 2. One may ask similar questions for P not equal to 2. We haven't spent time on this one right here, and therefore definitely this is a possible direction for research. Another remark I would like to make, and also it's a thing that is not quite the same as the scalar cases, that if you remember in Becquerel and Bonami's result, the boundness of the projection is equivalent to the boundness of the positive Bergman operator. While in the matrix weight case, that is not that obvious. If you recall what we had in the previous slide, we have an inequality basically relating the weighted norm of f to the weighted norm in a new weight case. Well, like I said, the submean value property is used. However, for general vector value function, we don't have that. Therefore, a similar estimate right here is not available for the positive Bergman operator. So far, we still don't know how to characterize the weighted space on which B plus is bounded. And also, one may ask similar questions about generalizing the result to the operator valued weight set. So I'm going to just think that's all of my talk, and I'm going to just stop right here.